So, goal of this lecture, we will prove one theorem. That will be all of the lecture. And formally, the theorem says that if you want to fit a classifier using some family of classification function with a certain number of parameters, then the number of samples you need to get good accuracy with high probability is the number of parameters. And this works for, in most cases, this number will be proportional to the number of parameters. Formally, it will be equal to the VC dimension. But this is combinatorial concept, and the goal, one of the goals of this lecture is to introduce this and then prove the result. So last lecture we introduced sample complexity. I will repeat what it is. It roughly states how many samples we need to obtain a good classifier with high accuracy. And we proved that the sample complexity is characterized by VC dimension. So it is VC dimension, which is roughly number of parameters that we fit, divided by the accuracy that we want to obtain. So it was proven in 2016 by Hanneke. But much earlier, this bound was known, and we will prove this bound in the lecture. Hanneke's proof is difficult, so I will not teach it. It would take an extra full lecture after this. So this bound uses this bound in the proof. So it's not known whether this also holds, so there is a big gap between these constants, like C is 1 over 30, and this E is 1600 or something. So there was a student for coursework who decreased it from 2000 to a bit smaller. Okay, so we will prove this bound, but let us first recall what it means. So let's go over how works our learning algorithm. How do we define risk? So what's the definition of risk? So we assume that we have a probability measure P over some input space X. We have some true classifier X from Y, and we have some training size N, which is natural number, may be equal to 0 in principle. And so what do? We generate a training set S using N random samples chosen from P. So we take them independently and identically distribute. So this IID, you see it often. Then supervisor will assign the labels of these inputs. So we will receive these training points with their labels. Xn. This is given to a learning algorithm, and the learning algorithm will output a classifier which maps X to Y. And then we want to have small risk. That means that probability, if we take a test point again according to P, then probability that that the true label differs from the one of the learned classifier should be small. So the risk, we use this funny notation that I introduced to make things explicit. So it is just the measure of points X where FSH of X differs from h of X. So, and now we can recall what's the definition of sample complexity. So sample complexity of a class of classifiers with parameters epsilon and delta is the minimal size of a training set, such that for all measures P, for all true classifiers in H, the risk, so probability over generating the training set, a bit more space. Let's write it here. probability over generating the training set that the risk of the learned classifier is bigger than epsilon should be at is at least epsilon should be at most delta. So minimum n for which there exists a learning algorithm. So I forgot one quantifier. So there exists, I will abbreviate, there exists a learning algorithm such that for all measures p and for all h in the class h, the probability that the learned classifier has risk at least epsilon is at most delta. Okay, this was a bit boring. That's good because it means that you all know this. So now let's now that we understand what is our goal, we will prove this. I will break the proof into two parts. So that will be chapter 7 and chapter 8 in the lecture notes. Chapter 7 is called growth function. We will define a growth function for a hypothesis class, which is a function from natural numbers to natural numbers. And in the first step, we will show that sample complexity of h, epsilon delta, is bounded by, we will use some funny value for delta. So we will prove that for every n, the sample complexity of, and here comes a formula, the growth function of 2n times 2 to the power minus epsilon n over 2. This is the floor. This thing with the brackets on the ground is bounded by n. So this holds for every natural number n. This first step of the proof. So now it's very bizarre and technical. Growth function is some combinatorial property of the class H. We will describe it as the number of, okay, I will soon say what it is. Second step, second part of the lecture, we will give a bound on the size of the growth function. So we will say that gh of n is at most e times n over p to the power p, where p is this VC dimension. And here we assume that n is at least p. So then this bound holds. And now these two results together will give us this bound. So that's the general structure. And how do they provide this bound? Maybe you can guess this. So we will substitute this function for g of n. We will substitute it inside here. So then we get an upper bound for delta. Then we will set n equal to this value. So what do we get here? We get an expression that depends on epsilon delta and VC dimension. And then some long simple calculus. So this huge expression, because there are 2 times n here. And n is a big expression. But after we substituted this huge expression, we can bound it by delta. So this will then be bounded by delta. So we will, well, we have n 3 times actually. So that's the inequality we then want to prove. So we set n to this value. Here we have 3 n's. Then we work this out, and we see that this becomes at most delta. So we know that this sample complexity is can only be larger than the sample complexity that we need. So here we will have, this sample complexity is bounded by this sample complexity with a very long delta, which is bounded by n. And so that follows the theorem. sample complexity bounded by this thing. So, okay, it's very abstract and boring. I just want to say that there are two parts. Okay. So let us start with the first part. First part is this thing. That will be the goal for the next 40 minutes. But I should say, what is this mysterious growth function? Well, I will wait a bit to say what is growth function. Let us do another proof, and then you will already guess what is growth function. So I forgot what I did last lecture. Did I say that sample complexity for finite h is bounded by
h minus 1 divided by epsilon z?
Yeah. Okay, so let's leave one out, truth bound. Let's now make a better bound for dependency on delta. So I will prove, let us start with h equals, with h of size 2. So let's imagine that h contains two functions, g and g tilde. And let us prove that the sample complexity is 1 over epsilon, ln 1 over delta. So, and we will follow the proof a little bit like for threshold functions. So, how does it go? Well, let us look to the definition. First, we have to fix a learning algorithm. It's our first step. So, any suggestions for learning algorithm? So, we will say fsh is equal to g tilde. So, any suggestions?
It means that actually that one of these functions, g or g tilde, is true. So we have to wait for a mistake and see which classifier.
Yeah. So we just pick a classifier that's consistent with the training set. And if they're both consistent, let's just say that he picks g. So let us pick g if for all examples in the training set, g of x equals y. So let us use this learning algorithm and g tilde if we have a point that contradicts g. Okay. So now let us bound the probability that the risk is bigger than epsilon. So if h is a function g, then what is its probability? So let us assume h is equal to g. Then probability over generating the training set that we output a high risk function is. Wake up. It's a very simple question.
Zero should be no. It should be 0, no?
Yeah, exactly, yeah. 1 is awake, okay. Yeah. So then it's 0. So then we are already finished. It's clear why it's 0.
If h is g tilde,
If h is g, then this probability is 0. Because we always pick this classifier. It will never happen that the training set contradicts g tilde. We are in the realizable setting. So this is our training set. That's how we define risk, always 0. So that was easy question. So we only need to think about the case where the true function is g tilde. So then we are in the problem if by coincidence all our training labels are consistent with g, but g is a bad function. G differs in a large measure from g tilde, right? Okay, so let's split it again in two cases. Now g tilde is true, two cases. Imagine that g and g tilde differ in a set of at most measure epsilon, or in a set of measure less than epsilon. Then we are good. It doesn't matter which one we output. our target is always true. Our goal is always reached, so we have probability 0 again. Okay, now let us assume that G tilde differs from G in large measure of points, at least epsilon. Now we are in trouble if by coincidence the training set only contains points where G and G tilde are equal. Then we will output the wrong function. So how can we bound this probability? So what's the probability that the first point, how can we bound the probability that the first point is such a bad point, where G and G tilde are equal? So we know that the first point, probability that x1, Gx1 equals G tilde x1. So we say that this is our assumption. P of the points x where Gx differs from G tilde x is at least epsilon. That's our assumption. Right? So this, by assumption, is...
minus epsilon.
Yeah. It is at most 1 minus epsilon. Okay. Now the probability that all points in the training set satisfy this inequality. How can we bound it? Okay, let me first write something technical. This is minus epsilon. Okay, now probability that the endpoints satisfy this condition, and they're taken independently. So this is this
power
to the
n.
power n, exactly, yeah. So probability that this condition is satisfied, probability that this is satisfied, all points of G tilde are consistent with G. G tilde is true function. It is bounded by 1 minus epsilon to the power n. So this inequality we apply to the power n. So it is exponent minus epsilon n. It's clear? Should I repeat?
No.
Okay. So, and then we are done because we want this to be smaller than delta. So I claim if n is large enough, then this inequality is true. How should we choose n? Well, let us set this equal to n. So then we have epsilon n is is bigger than ln 1 over delta, and then it works. So then we are done. Okay, thus for h has two functions. What if h contains a constant number of functions? Then we can get the bound, let's make a bit of space, size of h here. Even size of h minus 1. I'm not going to bother with the minus 1. Why is it true?
Because we have a true classifier and we have h minus 1 other classifiers, and
Yeah.
we already proved it for 1, so it's just going to be by the union bound.
Yeah, by union bound. And so we get h minus 1 by again ordering the classifiers and applying the union bound. We can say something stronger. If learning algorithm is consistent a proper learner, that means it just picks any function that's consistent with training data and belongs to h, then it will need this number of samples. So why? Regardless of which function the learner picked, we can look to all other functions, and each other function, for each other function we can define a set W of f, just the set of points where f of x is not equal to the true classifier. And we know that for each other function, if the training set contains a point from WF, then we are good. And so this probability can be now bounded by union bound as you said. So for a fixed function, the probability that we are consistent with this bad function is this value. The probability that it happens for some function in H, with risk at least epsilon, is bounded by the number of functions that have risk at most epsilon, and this is bounded by the number of functions in H. So then we apply the union bound, so basically we insert some H here and H here, and then we solve for n, and that means we just have to divide delta by size of H. Okay, so it seems clear. It's easy for most. Okay, then we are finished. And so what is important for us? It is, let us define like the class. I will use curly W. It's just all the sets WF for which the risk is at least epsilon. So for every set in this class W, our training set needs to hit such a point. Okay, so this works nicely for finite classes H. And there are some applications. For example, imagine we want to learn a conjunction. So the input space is bit strings of length D, and we want to learn a Boolean formula that's just an AND of several literals. Then we can bound. So we can bound the sample complexity of this task. So in many books there are very long proofs about this, but actually it's simple. These proofs are simple corollary of finite case, because the number of conjunctions. So the formulas. So X is mapped to the product of formulas of the form X2, not X5, for example. So X is a bit string. It means first bit times second bit times 1 minus fifth bit. So this will always be at either 0 or 1, because we assume X is a string of length D. So what's the sample complexity of learning conjunctions? For this we just count all possible conjunctions. And that's very easy. So what's a good upper bound for all possible conjunctions? So you should think about each variable.
2 power Z.
Yeah, but we also have negations.
3 power.
Yeah, 3 to the power D.
Why 3?
So either we have so we make a formula, and for each
no variable or
negation.
Not variable.
Yeah.
Okay.
Yeah, for each index, 3 possibilities. And so we fit it in, and then we know it's linear in the dimension, sample complexity. So it's very easy. So all clever people forgot about this simple bound. Well, not all, I guess, but all I've seen so far. Okay.
Can you please again recall what this curve W means? What does
Yeah. So it's just the set of sets.
sets of?
Yeah, and when we speak about set of sets, people speak about class of sets. Then there are 2 words. So a class is usually a set of sets.
What is the interpretation behind?
They're just a collection of sets that we have to think about. And the growth function, what will help us to make the number of such functions small. So that's why I gave the simple proof for finite case. Okay. So now let's start with real work. Let's define growth function. And then so I will delete them. This is too easy, you are already sleeping. But maybe on the video somebody wants to watch it. I've checked YouTube, and 4 people looked for, on average, 10 seconds. So all my effort to make this recording, and also it's like public for everyone, so that these 4 people might even run them browsers. So I don't know what, but okay, maybe if some people abroad or something start to actually learn. Okay. So growth function. I'm just gonna check. I've said everything here. Okay. So growth function was invented by Vladimir Vapnik, Alexei Chervonenkis, they're Russian guys, and they did this before 1968. So there are some traces of talks even a few years earlier. And people say it's the beginning of statistical learning theory, and Vladimir Vapnik is a person who pushed invention of support vector machines. And so when I was your age, it was the best learning algorithm. I mean, it was politically incorrect to say it was the best learning algorithm. Political correct answer was neural nets was the best algorithm. But for some reason, so like I applied for PhD grant, I said I will use not neural nets, but SVM. And then people said, oh, very good choice, because they were all smiling. But I had some excuse to use it. Okay, so just to say that there was a time that neural nets was not the best, and maybe it's possible such time will come again at some point. So if you don't want to learn about anything else, be aware that this is some risks. Okay, I've all said this. Okay, now the definition. I just want to show, to check the notation, that I'm consistent. Okay, so first, let us consider a set. You can think about a training set. So let us define a list of points, x1, x2, and so on, xn, or let's call it xk, in the lecture notes it's this, belong to xk. And we will apply all functions in our class H. So now I'm telling you what is this GH of, well, I will first define the number of dichotomies, and it's defined for this list. G tilde of x1, xk, and it is this. So what the idea, we apply all functions of H, and we see which labels we get. So we get them, they're elements of the set yk. So all labels on these k points belong to yk, and we count how many different sets of labels we get. So a dichotomy, so we fix a set, and a dichotomy is a set of k labels. Growth, number of dichotomies, just number of different vectors we can get for different functions. So let's write it formally. It is a set of fx1, f of xk. So now the question is, what is the growth function for threshold functions on S points? So can you tell it? So if the definition is clear, you can already think about this. F in H.
S? Yes.
Almost.
Maybe S plus 1.
Yeah. Yeah. So if H threshold, so if X is a subset, say, of Z, and size of X equals is S, then G of H threshold. Well, so it has an argument, so we need to be okay. So sorry, I said number of dichotomies I defined, but now growth function is maximum number of dichotomies for a list of k elements. So here is the second part of the definition. Is maximum number of dichotomies and so threshold functions on Z, if we take k points, then threshold function of k is exactly equal to k plus 1. Okay, what else do I need to say? Let's check some properties.
Can you explain why?
Yeah, so what is threshold function? And we don't need Z, we can, for R it's the same. So if we have k points, how many different vectors we can have? We know that above every one there must also be ones for threshold functions.
Yeah, k points.
Yeah. And so we can place the threshold on k plus 1 non-equivalent places, at the bottom and then above each point.
Ah.
So we get k plus 1.
Number of dichotomies is
Yeah.
number of places where we can place our classifiers.
Yeah. Okay, so let's now have interval classifiers and the real numbers. What's the growth function?
About S squared, but
Yeah, can you say it precisely? Because the form it will remind you in the very last moment of the lecture. It's good to say the precise formula in kind of some general way. Okay.
Okay, 1 for all minuses.
Yeah.
And we choose.
K choose 0 plus.
Okay.
So-
Yes, and
So now we have the question is clear, right? We have so the ones are on an interval.
plus
and the rest.
K1 and plus K2.
Yeah. K choose 2. It's clear why? So here we have sets of size 0. Here we have singletons. So always to pick 1. And here we have all sets of size at least 2. So that's growth function for interval classifiers. Okay, some elementary properties. Growth function of k is bounded by 2 to the power k. Why?
So for each k we have 1, 0.
No, all combinations. No?
Yeah,
No.
we check, it's the number of vectors. So we need to look at a set of k elements, and we can k times at most 2 labels. K is always at least 1. Why is this true? It's by convention. I said when I have H, then H always contains at least 1 element. So even if k equals 0, we have one list, the empty list. So this includes the case even G0 is exactly equal to 1. If H is a singleton set, contains only 1, then it's equality. And if there are 2 functions, then it will always be at least 2 whenever k is at least 2. Okay, this is very easy. If S is a subset, so imagine that S is a subset of S prime. What can we say about the growth function? So number of dichotomies of S prime and G, sorry, here is H. So monotonicity. Okay, here it's defined for lists. We can define it for sets as well. Just order the elements.
No, it's bigger.
Yeah.
Not less.
Yeah. So there is monotonicity in the argument. Oh, sorry, I did it wrong. Yeah. Yeah. There's also monotonicity in the function class. If h becomes bigger, then the growth function becomes bigger. It's all obvious. And now there is a funny property. Okay, so what can we say? What bound do we have when h prime? So imagine that there is a point x tilde, such that all functions in h map x tilde to 0, and all functions in h1 map x tilde to 1. What can we say about growth function of union? h0 union h1. Of some list. It is bounded by, so that's a property we will use at the very end of the lecture. So imagine that we have two classes, and then for one point, one class all goes to 0, for the other class goes to 1.
By this.
Yeah, by the sum. h0 of L plus g tilde h1 of L. Okay. That's enough for property. Okay. So that's
what if, for example, for this point x delta, our h0 also would map to 1? What if h0 and h1 both map x tilde to 1 or to 0? What's both? Both.
Oh yeah, it's always true. Yeah, actually, yeah. Good point. We don't need this complicated. Yeah, good point. So basically we have equality, right?
Yes, in this case it should be equality, no?
Yeah?
It should be equality in this particular case.
Yeah, it's true with equality.
Shall we prove it?
It should be true with equality. But we need one more point. We can do it like this, I guess. M plus 1, and this is M, and then this equal. Or let us use N to be consistent with notation a bit. No, that's not true either. Okay, sorry, I cannot invent an exercise. I should. Okay. Okay, sorry for this silly example. Let's delete it. And let's. Oh, what is the time, by the way?
5.
It's 5.
5, like exactly 5.
Okay.
1 minute.
Yeah, the problem is I cannot check time on my phone because it closes the. If I switch the screen, then. Okay, and now we let's go back to our goal. Let me write it again. So this funny thing I wrote, that sample complexity of epsilon growth function of 2n times 2 to the power minus epsilon n over 2. Actually, I forgot the 2. Is at least n. So that is proposition that we're going to prove now. And the first step of the proof actually doesn't have to do anything with growth functions. I should have said it before I said what it is. So First, so the first lemma will just say that, so what's the problem when we consider, for example, threshold functions? So we got a proof that bounds the sample complexity for finite sets. Now we go to imagine threshold functions. They have very small VC dimension. And so we hope to get a good bound. And we proved the good bound last lecture. But we cannot apply this trick with union bound because we have infinitely many threshold functions on the reals. So what we will do is we will transform our problem from infinite set H to a finite set. And how we're going to do this? Instead of looking to the risk of our classifier, let's generate test set. And let us think about how many errors our classifier makes on the test set. If the learned classifier has high risk, then with high probability, we will have many errors on the test set. And so let us bound the probability that we have many errors on the test set. Because if we have bad classifier, we have many errors with high probability. So to bound this probability, we just have up to a factor 2. So what I want to say is that we will prove that probability that we make many errors on the test set. Oh, I'm using this. So W is the class where our learned classifier is wrong, and we want to bound the probability that we make more than epsilon over 2 errors. So that's our plan, we will bound this where we generate T similar to S.
Why is epsilon over 2?
Eh?
Why it is epsilon over 2?
Well, if our classifier has risk epsilon, then it's likely that we get epsilon 2 fraction of mistake.
Ah, okay.
So we take a little bit larger to get a good conditional probability. So in the first step, let me check that I don't waste time. In first step, I will say that now I screwed. Click someplace. Probability that WFSH is bigger than epsilon is bounded by 2 times this probability. So that's the first lemma. So here is error that the learned classifier, probability that a learned classifier makes a mistake. And we will prove that this is, and I need to say it precisely, so we will use this thing. So probability that our classifier is bad, this is precisely the risk here. So and here I use this set WF. So why is it true? Okay. So what I'm using here is that, let us call this event A, let us call this event B, and I say that probability of B is at least probability of A given B, no, B given A, times probability of A. Right? Because here is probability A and B. So that's what we use. Okay. let us be pedagogical. Okay, and so what I only need to prove is that this is bounded by 1/2, and then we are done, right? Because we have 1/2 probability of A is at most probability of B. So, sorry, that this probability is at least 1/2. Okay, so I need to have the lower bound. B happens with probability at least 1/2 if A happens. So this needs to happen with probability at least 1/2 if this is true. But okay, let's take n points from the test set independently. What is the problem? Probability that at least n epsilon over 2 times we pick a point from this bad set. So it's binomial distribution. Expected value of each sample, so probability is at least epsilon, and then we apply some kind of law of large numbers. So here we take n independent experiments, and then there is success with probability at least.
Binomial distribution with probability epsilon.
Yeah. And n repetitions, and for each repetition there is at least epsilon probability that it works. And now I want to prove that with probability 1/2, we have at least 1/2 of the expected value. And so for this, let us look at a number of successes. Let us look at the distribution of binomial function. And so, so there is a maximum around the expected value of binomial distribution. And we are interested in proving that so here is our bad region, that the experiment does not happen, that we have too few successes. And I want to show that this is at most half of the thing at the right. Actually, for binomial distribution, it is this rounded down. It's true for this rounded down, but we use something weaker, and we get it by noting that the distribution increases here. So we look at a point, and before this point it increases. It increases up to the expected value rounded down. So when we go to half of the expected value rounded down, we take half of an area. So we see that this area can only be smaller than this area. And so this must be smaller than half of everything. And so that's how we prove that this must be at least 1/2. Probability of seeing enough failures on the test set is at least 1/2. And so that's the first lemma. Okay. Now we need to prove second lemma. Let me remind what it is. By the way, on the colloquium, you will also, if you need to explain this proof, you will get all the lemmas. So you can look at previous year. There is a text, the question of colloquium. It will be very similar this year. There is just like 1/5 of the well, the 4 last lectures is new material, and 1 additional. So. But for these lectures, they've already been in previous year, and the colloquium questions are the same. Okay. Now, let's go to the next lemma. So we will need this lemma later. Let us write down the next lemma. Okay, what's the whole idea of the new lemma? Imagine that here we generate 2 sets, S and T, right? Of size n. Let's now generate a set of size 2n at once, and then randomly split them into 2 sets. That will be the idea when we combine both lemmas to get this. So now the second lemma considers the generation of a set. So the second lemma fixes a set U of size 2n. and then considers probability that when we learn on one half, we make many mistakes on the other half. We will say that this has small probability. So here we say ST is a random splitting of U in two halves. So randomly, so basically we only need one half. Randomly select half of U. And then probability over this random selection that W FSH intersect U is bigger than L. So probability that we make many mistakes. So this is the learned classifier. Probability that it makes many mistakes on U is smaller than G to N times 2 to the power minus epsilon N over 2. So here is next lemma. Sorry, here we will put 2 to the minus L. Did I write it correctly? Yes. And that's what we have. Okay. So for this to happen, we need a classifier that makes at least L mistakes in U.
U, which is
Yeah.
x to
Yeah.
size to n.
Yeah. Okay, sorry. Here I will fix the learner. Actually, this bound will be achieved for any proper consistent learner. Because we will get this for any proper consistent. Do you remember? Proper means output is always a function from the class H. Consistent means 0 errors on the training set. Okay, for every proper consistent learner, this bound holds. Why? Well, in order for this event to happen, U must contain at least L elements where some classifier makes a mistake. So let us fix.
Can you repeat what is proper?
Proper means output is a classifier belonging to a class H. Okay. So for proper consistent learner, for this to happen, there must be a classifier in H that makes at least L mistakes. So now let us think about all the classifiers that make at least L mistakes. Let's pick one of them. Let's think about one of them. In order for the learning algorithm to produce this classifier, it needs to pick elements where, so S must contain all elements outside this mistake set. Because it's consistent learner. It will never choose this classifier if it contradicts some input-output pair of the training set. Okay, now when we take a random half of S, we need to bound probability that this element, that S does not contain elements from W. So here, what is this? We have a bag, U. We need to select, so there we assume that there are at least, so that there are elements, but there are L-bed elements. And now we select random half, and we need to bound the probability that this random element does not contain any bad elements. And this you should remember from seminar. There was an exercise. Imagine you have a bag of elements as even. You select, there are L-marked objects. Select random half. Probability that you have no marked objects is at most 2 to the minus L. So it's very easy to prove this. But let me skip it, otherwise I will need to go over time. Okay. So here, U is the set. Marked objects are misclassified points for our fixed classifier, so they are WF. And so probability that F can be an output of our learning algorithm is at most 2 to the minus L. But that was when we thought about one fixed classifier that makes at least L mistakes in U. Now we need to think about all classifiers that make at least L mistakes in U. And we need to apply it to all classifiers. There can be infinitely many, but it's not a problem to apply union bound. Why?
Because we're thinking about mistakes.
Well,
So,
we think about subset of U.
which maximum can be 2n size, and each classifier can make at most 2n mistakes. Is it?
What do they?
No, we have to
only J actually have distinct classifiers.
yeah, but we can do better than 2 to the power n.
No, I mean a G of 12.
A 3 of
G of 12.
G of 2n.
G, yeah, G of 2n, yeah, exactly. We only have to think about G of 2n mistake. So we only have to think about possible sets WF. Yeah? So we only have to think about all dichotomies in U. So we only have to think what the functions are doing inside U, in other words. So when we apply the union bound, we can group all functions that have same labels in the set U. All functions that are equal in U, they are together. And so how many different behaviors in U we have is precisely growth function. So in conclusion, for fixed function that makes at least L mistakes on U, we have bound 2 to the L. For example, if H contains two functions, like in the beginning of the lecture, we get bound 2 to the minus L. But otherwise, we apply union bound over the growth function. And so for each function f, so for each dichotomy on U, we apply union bound, and we get this bound. So this lemma is proved. So we have two lemmas, and together they imply this thing. Sorry, is proof of this lemma clear?
It's not clear when we go from one classifier to follow the classifiers.
Yeah. Okay. So indeed we need to apply all classifiers. But here we are only thinking about the set U. So if two classifiers have the same behavior inside U,
We merge them.
we merge them. And so we only have to think about different behaviors inside U.
Okay.
And the dichotomy of U is number of behaviors inside U. And so this is number of dichotomies by definition. It's an upper bound on number of dichotomies because U has size 2n. So that's. And now the last step, why these two lemmas imply this. So it's already clear.
No, take L equals to L epsilon.
Yeah, so L will be equal to this. Then we have, so then this bound will be precisely this thing. This will be our delta. So we have, sorry, I forgot the 2 here. Because here we have a 2. So this probability, we upper bound by this. But to do this, here is something different. Here is, oh, T intersect. Nobody sent anything.
I kept it for later.
Yeah. Okay. So now there is an issue. So if we set this L equal to this value, this is almost the same event. But here we have T intersect WFS, and here we have WFS intersect U. Here we have
But
U and
W intersect S is empty. So
Yeah, yeah,
it's
yeah.
equal.
yeah, because there are no mistakes on S. And so if we subtract S from U, this value doesn't change. So we use S for training, T for testing. And here we look to, this is equal to S union T. But there are no mistakes on S because the learning algorithm is consistent. Okay, so this event is the same as this probability. So probability of having high risk classifier is at most 2 times this probability. And for L equals this, we conclude this. Okay. So this was first big step of the proof. And now I'm scared, only 25 minutes left, I'm afraid. Is it right? What's the time?
It's 20 minutes left.
20 minutes left, okay. So now I need to, but this is very beautiful proof now. Okay, so if we see dimension, so we say that a set S is shattered. I will define VC dimension. And then, okay, so what is main result of this part? Yeah, I'm afraid I will need 10 minutes more and then it's still quiz needed. Do you need to go somewhere? Okay. I will create lectures where I have 10 minutes early stop to compensate more. Okay, but now we will do all of the proof. So now we will study growth functions. We will study this function. And there is a very remarkable property that explains why we can have this worst case guarantee result, this sample complexity on it, because it's very powerful. It works for all input distributions. So even if your worst enemy gives you a distribution, you can apply it. Okay, and now we go to the core why we have this very strong result. This is because growth function is either bounded by a polynomial or it is equal to 2 to the power n. That's the only thing. There is nothing in between. So growth function is either equal to 2 to the power n for all n or bounded by poly n. Nothing in between. It's completely mind-blowing. For every set of classifiers H. So, and moreover, is bounded by a very nice polynomial, n plus 1 to the power VC dimension of H. Okay, so let us prove this result. I need to say what is VC dimension. VC dimension is the first point where growth function is not equal to 2 to the power n. So the smallest argument where this is false, minus 1. I will give other definition. So we say that the set S or the list S is shattered. No, let us say set S is shattered if all dichotomies appear G tilde of S is equal to 2 to the power size of S. So the set is shattered if we can see all possible dichotomies. And the VC dimension is the largest side of shattered set. Is max of size of S, S is shattered. Okay, let us do an example. What is VC dimension of interval classifiers? So again, we have a line, and the positive examples, they are those inside a certain classifier, and otherwise we have minuses. So what is VC dimension? So to know VC dimension, to get lower bounds, we need to find sets that are shattered. So can I shatter a set of one element? That means, can I have both labels on one element? Of course, if I take a point here, then I can get both plus and minus. Plus when the interval is over, minus 1. So when I have 2 points, can I have all dichotomies? So we need to have plus minus, minus minus, minus plus, and plus plus, and that's easy, right? plus plus if we're over it, and so on. Can we have 3 points? Can we shatter 3 points?
No, we can't plus minus plus.
Yeah, exactly. So
VC is 2.
yeah. So regardless how we choose 3 points, when we order them, we can never do plus minus plus. So for all sets of 3 plus 3 points, so to prove, here we have equality. So to prove lower bound, it's easy. We have to find one set. To prove upper bound, we have to check all sets. Every year on exam, there is someone who does the opposite. So he said there is one set that cannot be shattered, so the VC dimension is at most so much. No. To have upper bound, you need to check all sets of size 3. Okay, so let's do some examples of VC dimension. Okay, my battery is gone. So let's remember which one I should discuss. So let us have so interval classifiers. Okay, boxes in the plane. Oh, sorry, I deleted the definition, but you remember it, right? So now we have inputs x equals r squared, and the pluses are those points inside the box. So a generalization of interval classifiers. What is VC dimension? So let us try to find, to shatter a set of size 3. Can you shatter a set of size 3? So that's easy. I think if we have 4 points like this, then we can get all labels. So clearly if there is one plus and the rest is minus, then we just put a box over the plus and the rest is minus. So here we have pluses, outside the box minuses. If there are 2 points, yes, we can also do it. Like put a box here, if these are plus, and minus, if these two are, if the two in the middle are plus, we put a box here. So 4 points can be shat. If we have 3 pluses, no problem. Okay?
And if we have points like that create an orthogonal triangle, a triangle,
yeah,
with,
like this.
yes.
So, but that's 3 points.
And like opposite points are plus and with
Yeah, then we have a problem. But to get lower bound, so recall the definition, I shouldn't delete this, but VC is equal to max size that can be shattered. So H shatters S.
So we find an optimal S.
Yeah. So to understand that the VC dimension is large, we have easy task. We just have to find one set that's shattered. So your set is a bad set.
Okay.
It doesn't help to show it's large. And the natural thing is to just find examples to make it large. And if you find no examples anymore, then show your example is the best one. So we have find 4 points, so we don't need to think about 3 points anymore. And we know that VC of boxes is at least 4. Okay, it's correct bound. 5 cannot be shattered. Why 5 cannot be shattered? Okay, sorry, I will explain to you. It's hard exercise. So there are 2 cases. No, 2 cases. So let us look. So we have 5 points. They are anywhere. 1, 2, 3, 4, 5. Now let us. So let us look to the maximal. Recall this let's look to the smallest box that contain all positive examples. Well, let's do something similar. We have 5 points, and let us look to the smallest box that contain all 5 points. Okay? So when we move a line upward, at some point it will touch 1 point. Let's put it here, this point. When we move the line from right to left, it will touch a point. And from every side, we will touch 1 point. So we will touch 4 points. Let's make these points plus and the 5th point minus.
But the last one also can be on the side or
Yeah.
in the...
But that's also fine for my proof. So if the line touches 2 points, pick 1 point of the 2. Okay? And all the points you picked, let's set them plus and the other one minus. And then we cannot make this dichotomy. Okay? Because this point is in the inside or on the border. But that means it must be plus. So that's how we find, so when we prove upper bound, it means for every set we have to create a dichotomy that we cannot make. So it's the hardest job. Okay, what else do we have? Half spaces in plane. So what's VC dimension? So again, x r squared, and now half planes. We draw a line, one side is plus, the other side is minus. What is VC dimension?
3.
Yeah, good. Very good. So let's think about this. Oh, my main theorem is gone. So we can take any 3 points that are not on a line and we can shatter them. Can always separate one from 2 others. Okay, so fine. Now let's think about 4 points. There are 2 cases. So either 1 point is in convex hull of the others, then these points cannot be shattered. What should I take as dichotomy?
Plus is for
Yeah,
border.
yeah. The internal point I put minus, so this point is in convex hull. That means for half space, if a point belongs to one side of a half space, another point belongs to the same size, then all points between these points, if this is plus, then all this segment is plus. So for half spaces, if a bunch of points are plus, then any convex combination is also plus. So this doesn't work. Now, second case, if the 4 points are not convex combination of each other. So which dichotomy will I make?
Opposite one.
Yeah. And that's for the same reason, right? I look to the convex hull of these 2 points and the convex hull of these 2 points, and this point should be both plus and minus. It's not possible. Okay. And so there is more general result. So if x is equal to Rd, then VC dimension of half spaces through origin is equal to D. So, and proof is short. Let's do it quickly. So I forgot the name of this theorem. So half space is through origin. I forgot to write through origin here, but you got it. That's right. So, okay, let us take D plus 1 points, x1, x2, and so on. xd plus 1. So we have this list of points. We have d dimensions, so one point is linear combination of other points. So we can select, let's say it is the first point, or it's the last point, xd plus 1 is equal to a1 x1 plus ad xd. So now I create a dichotomy using, and I will use, I will say that I will consider the dichotomy yi equal to the sine of ai. So I use labels -1 and +1. Yes? So let us look. So now let us consider any half space. And I claim, okay, and here I also need to assign a label. I will -1 will be the label. So now I claim that every half space that has these points correct will have this one wrong. Oh, you already understand it. Everyone? That would be great. No, not everyone. Okay, so how does it go? So we let us consider a W half space, and it has these d points correct. So we know that W x1 is equal to y1, which is sine of a1. So what happens with, so we know that sine of this equals sine of a1. And the same is true for second point and so on. So we know that this, so let us look now to W xd plus 1. I claim that the sign will also be zero, at least will be positive. Why? So well, we need to apply the dot product with W here, and the sign of each term is plus. So the sign of this is also plus. Okay, so here we have a1 w times x1, right? Since w is correct on these points, we have that this holds. Sine of this equals sine of this. This product of signs must be positive. So all the signs of these terms are positive. They're all at least 0. But we need that this is classified to -1. But that's impossible, because we cannot have sign, this cannot be smaller than 0. So this Radon theorem it's called. So Radon theorem, if you see of half spaces through origin, is equal to D. Oh, I forgot to say why we can shatter D points.
Just
Yeah, standard basis.
yes.
Yeah. So standard basis can be shattered.
Any basis.
Yeah, and even better, yes. Okay. Now what about half spaces not through origin?
D plus 1.
Exactly, D plus 1. So again, standard basis plus 0 can be shattered. And to get upper bound, well, we can just, half spaces through origin is the same by augmenting by one coordinate. So put a 1 under all your points, and then you have, so classification, so you can always get rid of the constant term by creating extra coordinate. Okay, but this is just some examples. It's possible that, very often, VC dimension equals number of parameters, or is very close to the number of parameters. So neural net with S weights will have, and threshold classification will have VC dimensions S log S. So very close to S. But sometimes one parameter is enough to get infinite VC dimension. Its homework task is an example, but it's kind of strange example. Another example is sinus functions. So when h is equal to the class of x goes to the sine of sinus functions nu x. So, and the input spaces are, and y is still this. So this one has, so there is only one parameter nu, it has infinite VC dimension. So, but I don't have time to tell you the proof, it's a bit technical. So you can make your function oscillate very fast, and if you oscillate fast enough, you can fit any values that are very close to the origin. Okay, and now the very beautiful proof that either Gn equals 2 to the power n, or is bounded by n plus 1 to the power Vc of h. Okay. So we will prove it by induction on n. So clearly if n is equal to 0, then everything is okay. Because if n okay, so I will, so when n is smaller than Vc dimension, then we have 2 to the power n for the growth function by definition, right? So if we have infinite Vc dimension, then we have this value. Otherwise, we will look at points with finite Vc dimension. If n is 0, then g of n is equal to 1, because we only have empty list as dichotomy. And so then this bound is good. Now let's assume it's true for some n and go to n plus 1. So let us look about to some list of n points. And we know that number of dichotomies of this list is bounded by n plus 1. Yes. Now let us look to n minus 1 points. And then it is bounded by Vc of h. Now we will look at point n plus 1. So let us look at all possible dichotomies.
Just n, because we have n minus 1 before.
Yeah, so here we have n plus 1, but now I look to n minus...
Not n plus 1.
yeah, so yeah, good point, yeah, okay. Okay, so let's do example for n equals 3. So then we have like 4 dichotomies, 0, 1, 1, 0, 1, 1. And now point number 3 arrives. That means that some dichotomies, they might split. So we can have this thing, 0, 1. But maybe other dichotomies might not split. So in this example, so here is the class H. When we have 2 points, we have 4 equivalence classes, right? So when we look to x1 and x2, so just forget about blue for now. Before when we look at 2 points, we have at most 4 in equivalence classes. So in this example, we have all 4 of them. Now x3 arrives, and it might happen that for this class, x3 is all the same value. It might be 1, and here it might be 0, for example. Okay? But here, it might happen that some functions that are 0 on x1, x2 are also 0 on x3, and some are 1. So in this case, number of dichotomies increases. And there are 2 types of dichotomies. Those where the new value is fixed, and those where we have both cases. So now let us define the class H prime, of all functions where the dichotomy splits, but the function is equal to 0. So for all dichotomies that split, let us look to the functions on one side. Let's say the 0 side. So let us look to this class H prime. So it is this class of all f and h, such that f of xn is equal to 0, and there exist g and h such that g of xn is equal to 1, and g is consistent with f on all the other points. And gx1 is equal to fx1, and okay, so this is a long definition, but let us say that so I call it functions that have a mirror. So functions, so the mirror is j. J has opposite value in xn, but has the same value as f in all other functions. So this is our special class H prime, and this is the clue to our proof. Because I claim that number of dichotomies of H on x1 till xn is equal to number of dichotomies that we had before on the first endpoints plus number of dichotomies of H prime on the n minus 1 points. So it is number of dichotomies on xn minus 1 plus number of dichotomies on H prime of x1 xn minus 1. So that's the claim. So all the new dichotomies, they're equal to either an all dichotomy, so an all dichotomy plus a 0 appended, plus a 1 appended, or a dichotomy of H prime. And H prime contains only zeros in the new point. So basically, I split the dichotomies using the last point.
It's quite obvious.
It's kind of obvious, but I wrote this complex definition. So should I repeat? So one says no, but the rest says nothing. So let me say it again. So what is number of new dichotomies? The ones in blue. It is number of all dichotomies plus the number of dichotomies that split. Okay. So here we have number of all dichotomies. That's old. And here we have new dichotomies. Why do we have new dichotomies? I fixed the value, so for those who split, so for those where the new value is fixed, they don't have an element in H prime. So if f belongs to this quadrant, then the value is fixed to 1 or to 0. But then it cannot go into H prime. Only these functions from here may go to H prime. And those that are equal to 0 will go in H prime, but those that go to 1 do not go to H prime. So number of dichotomies equals all dichotomies plus dichotomies of H prime on n minus 1 points. So we have equality here. So now we are ready so what does it say? Let us, we will bound this. So now let us apply induction hypothesis because we have n minus 1 points. So here the first term is bounded by n to the power Vc of h. And the second term, well, for the second term we have to think about Vc dimension of h prime. So I claim that Vc dimension of h prime is 1 smaller than Vc dimension of h. Why is it? It is because I fixed the value on xn equals 0. And h prime, so when we add all the mirrors, then Vc dimension of h prime will increase by 1. Because for every shattered set, we can add xn. It's still shattered, because h prime only has dichotomies that split. So, so Vc dimension of h prime is 1 smaller. This is a crucial step. It's the only hard step. The rest is just definition. Okay. So then this thing is bounded by n to the power Vch minus 1 by induction hypothesis. Okay, so here we have that this is bounded by n to the power Vch plus n to the power Vch minus 1. Okay? And this is bounded by n plus 1 to the power Vch. And so we get an n plus 1 we can put in the front, and then we only increase it. So that's proof. That's magical proof. N plus 1 to the power Vch.
When we replace the polynomial with its estimate.
Yeah. So you know growth function by its estimate.
Plug the numbers and solve for delta.
Plug numbers, solve for. So you mean after we've proven this?
Yeah.
Yeah. So now, plug the numbers, solve for delta, yes. But this bound will give you something slightly weaker. So there is a second bound, but I will not prove it because it's too late now. But you can learn it yourself because it's also just computation. It's also very beautiful. So the second, well, I can quickly say, this proof actually gives something stronger. It says that number of dichotomies of a set is bounded by the number of subsets of the set that are shattered. So there is magical lemma. Now I can remove this because we don't need it anymore. There is a stronger lemma. It's in the lecture notes. So it says something stronger. Well, but actually I can give even a, but then it's technical. No, but this lemma I think is very beautiful. But some people say it's ugly. So it says that G tilde of a list L is bounded by the number of subsets T of S, H shatters T.
Maybe instead of L, we should use something.
Yes, I forgot. Yeah, so here should be S. And a corollary of this lemma is that G of n is bounded by sum of polynomials. N choose 0 plus n sum of combinatorial coefficient VCH. Because we know every subset has at most VCH elements. Every subset that's shattered has at most VCH elements. And now we need to add this coefficients.
Yeah, so same formula we had
Yeah.
when we have intervals on the line.
Yeah, so we can bound it by n plus 1, but it's also bounded by e to the power n of k to the power k, where k is equal to Vc of h. So this sum is bounded by this. It's a short proof actually. So sum of n choose I equals 0 to k. It's small. Well, it is true if n is at least k. So n at least k, then this inequality holds. And why it's true? So this is at least. So let's multiply each term by n divided by k to the power k minus I. So let's multiply by this. So this is something that's at least 1. Okay, so then what do we have? Let's put n over k in the front. And we have sum n choose I times k over n to the power I. Okay, and so what is this? This ni is bounded by n to the power I divided by I factorial. So if you're from other faculty, you need to check this, but it's not so hard. And so when we apply this bound, what we see is that this n falls out, and what remains is I factorial. So this is equal to n to the power n over k to the power k, and what we have is ki divided by I factorial. And I starts at 0 and ends by k. But if we go to infinity, it's just bigger. And this you know, right? It's Taylor of exponent of k. So we have is equal to n over k, e to the power k. It's precisely this bound that we want to prove. And so this is bound on the growth function. If we substitute this one into this value and solve for delta, we get the theorem. So it's, well, it's worked by Ehrenfurt, Wasser, blah, blah, blah in 1989. But I think if somebody asked Vapnik and Chervonenkis 30 years ago, they could come up with this. Because all the techniques, all math was already invented by them. Okay, so now let's stop.